So what we're going to do in this video is we're going to take a look at simplifying some expressions with I. So we'll start with just some very basic expressions. 3i minus 6 plus 2i minus 12. Okay, so I works similarly to how any variable would work. We're just going to combine like terms. So 3i and 2i make 5i, negative 6 and negative 12 make negative 18 plus 5i. You'll notice that I'm writing the negative 18 part first, followed by the 5i part. So the negative 18 is the real part of my complex number, and the 5i is the imaginary. So when I write my solution as a complex number, I'm always going to write my real part followed by my imaginary part. So another similar example, if I have 2i plus 6 minus 3 times I minus 2. So I'm going to start by distributing the negative 3, negative 3i plus 6, combine my like terms, so I have 12 minus I, and that is simplified as much as it can be. And so adding and subtracting is just very easy. You're just combining your like terms, okay, and you cannot combine your real numbers with your imaginary. Same is true for multiplication. 2i minus 3 times 4i plus 6, okay? Very much the same idea. The only thing that we have to remember here is I is equal to the square root of negative 1. So I squared must equal the square root of negative 1 squared. What to remember about the job of a square root and a squared is that they undo each other. So I squared is actually not imaginary at all. I squared is just negative 1. So if I remember this fact and then go over and use FOIL, the distributive property, 8i squared plus 12i minus 12i minus 18, I'll get 8i squared minus 18, but I squared is negative 1, so I get negative 8 minus 18, so in this case I'll get negative 26, just a real solution. Try something like that again. 4i plus 1, 3i minus 3, so 12i squared plus 3i minus 12i minus 3. So you can certainly, and most of the time, you will get a complex number when you multiply two complex numbers. So I want to do this second example just so you saw that my answer was complex, whereas in my first example, my answer was a real number. This is a little bit of an unusual example. Okay? Very typical example would be if I had 2i minus 6 times 2i plus 6. I can tell right away that my answer here is going to be a real answer. And that is because I am multiplying some complex number by its conjugate. Okay? And the conjugate just means that the expressions are the same. The difference, and I really should have written this in the form 6 minus 2i, 6 plus 2i. The difference in the conjugate is the sign of the imaginary part. So the expressions are the same, but the sign in front of the imaginary part is different. Anytime I multiply a complex number by its conjugate, I'm going to end up with a real answer. So 36 minus 12i plus 12i minus 4i squared. 36 minus 4 times negative 1. 36 plus 4 is 40. Okay? So understanding the relationship between a complex number and its conjugate is an important one, because from time to time we'll have a fraction with a complex number in the denominator. I really need to get into that habit of writing the real part first. But you'll see we have a complex number in the denominator, and what we learned earlier in the year is that you cannot have a radical in your denominator ever, and I is replacing a radical. So really, my denominator is not rational. We need to get rid of that radical in our denominator. We do that just by multiplying the numerator and the denominator by our conjugate. Because as we saw earlier, if you multiply a complex number by its conjugate, you're going to get a real number. So my numerator, I'll get 3i minus 6 times 2 plus 3i, which is going to equal 6i minus 12 minus 12i minus 18 plus 9i squared. So let me just check that. 6i minus 12 minus 18i. Knew I did something wrong there. Plus 9i squared. All over is 2 minus 3i times 2 plus 3i. So it's going to be 4 minus 6i plus 6i minus 9i squared. So my numerator is going to be negative 12 minus 12i plus 9 times negative 1. My denominator is going to be 4 minus 9 times negative 1. So I'll get negative 12 minus 12i minus 9 all over 4 plus 9. Negative 21 minus 12i all over 13. And now, if I really wanted to, I could write this as a complex number by writing the real part followed by the imaginary part. So this concept of the conjugate helped me to make my fraction so that there was no longer an I in the denominator. And that's my work there for dividing complex numbers.